Okay, let's dive into this. Have you ever just stopped and really wondered what everything is made of? I don't just mean the big stuff like stars and galaxies. I mean everything right here, right now. Your desk, the cup of tea you might be drinking, the air in the room, even you. It's all just stuff, right? But what is that stuff really? What is it at its most fundamental, most basic level? Well, that's exactly what we're going to unpack together today.
Just take a look around you. Everything you see, everything you can touch, scientists have a simple word for all of it: matter. It's a pretty broad term, isn't it? I mean, how can a fluffy cloud and a solid brick both be matter? What's the connection? That's the big question. What's the secret recipe that makes up our entire world? Let's start breaking it down.
So, here's our game plan. First, we'll look at the world as we usually see it, which is mostly made of mixtures. Then, we're going to get a little picky and see what scientists really mean when they use the word pure. After that, we'll get to the heart of it all: elements and compounds. And finally, we'll tie it all together to see why this isn't just some textbook lesson, but why it's absolutely crucial to, well, everything.
All right, first things first. Let's talk about mixtures. Honestly, almost everything you interact with every single day is a mixture of some kind. It's the most common way matter hangs out in the world, as a jumble of different things all sharing the same space.
Now, this is the most important thing to get about mixtures. The things you mix together, they don't actually change into something new. Think of it like a party. You have all your friends in one room. They're all mingling and sharing the same space, but each person is still themselves, right? Your friend who loves to dance is still a dancer, and your friend who tells jokes is still a comedian. In a mixture, the ingredients are just like that. They're hanging out together, but they all keep their own original properties.
And this is a perfect and delicious example of what we call a non-uniform mixture. In this poha or this salad, you can literally see the different parts. There are the peanuts, the onions, the coriander, the sprouts. The components are not evenly spread out, which means every single bite can be a little different. One bite might have more onion, another might be all sprouts. You know exactly what I mean.
But then you have the complete opposite: uniform mixtures. Imagine stirring some sugar into a glass of water. After a moment, where did the sugar go? It looks like it disappeared. But of course, it didn't. The sugar particles are still there. They've just spread out so perfectly and evenly throughout the water that you can't see them anymore. Every single drop of that water now tastes sweet. That's a uniform mixture. The air we're breathing right now is another perfect example. It's a smooth, uniform mix of nitrogen, oxygen, argon, and other gases.
Okay, so we've got mixtures sorted. Now let's tackle a word that we use all the time, but that has a very, very specific meaning in science. The word is pure. We see it everywhere, right? Pure orange juice, pure honey, pure cotton. But what a scientist means by pure is probably not what you're thinking.
This is a fantastic example of that difference. When we see a tin that says pure ghee, what we understand is that nothing extra has been added. It hasn't been adulterated, which is great. But if a chemist were to look at that ghee under a microscope, they wouldn't see one pure thing. They'd see a complex mixture of different types of fat molecules, some water, and other substances. So for a scientist, this is definitely not pure.
So here's the scientific definition. For something to be a pure substance, it has to be made of only one type of particle. That's it, just one. Imagine a massive bag filled with trillions of identical marbles. That's a pure substance. And critically, you can't separate it into different things using physical methods like filtering or picking bits out. You're stuck with that one single thing.
Now, this is where we get to the real foundation of it all. It turns out that even these pure substances come in two different flavors. We can sort them into two final categories: the absolute fundamental building blocks, which we call elements, and the things that are built from those blocks, which we call compounds.
Let's take water as our example. Water is a pure substance, right? Every particle of water is identical to every other particle, so you can't filter it into different parts. But can we break it down using a more powerful tool? Not a physical tool, but a chemical one. The answer is a big yes. We're going to use a clever process called electrolysis to see if we can literally split water apart.
The setup for this is actually quite simple. You take a battery, you put it in some water, and you pass an electric current through that water. Then we place these test tubes over the battery terminals to catch any gas that might be produced. The big question is, what is that gas? Is it just steam? Let's find out.
And there it is! As soon as the current is on, you can see bubbles streaming up from both terminals. But wait, look closely.
something really interesting is happening. Do you see how one test tube is filling up with gas way faster than the other? In fact, it looks like it's collecting about twice as much gas. That's a huge clue right there. And now for the big reveal. We take the test tube that filled up with more gas, bring a lit splint to its opening, and pop. You hear that distinct little popping sound. That is the classic surefire test for hydrogen gas. The gas in the other tube, by the way, would make the flame burn much brighter, proving it's oxygen. So think about what we just did. We took one pure substance, water, and we split it into two completely new and different pure substances, hydrogen and oxygen.
And that brings us to the definition of an element. Hydrogen is an element, oxygen is an element. They are pure substances that are the end of the road. You simply cannot break them down into anything simpler using chemistry. They are the ultimate building blocks of the universe. Think of them as the Lego bricks that everything else is made from. So if hydrogen and oxygen are the Lego bricks, what is water? Well, water is what you get when you click those bricks together. It's a compound. A compound is a pure substance that forms when two or more elements are chemically bonded together, and they always combine in a fixed ratio. For water, it's always 2 parts hydrogen to 1 part oxygen, H2O. And here is the truly amazing, almost magical part about compounds. They have properties that are completely different from the elements that make them up. This is so important. Think about it. Hydrogen is a highly flammable gas. It's used as rocket fuel. Oxygen is the gas that fires need to burn. But when you chemically combine them, you get water, the very substance we use to put out fires. It's a completely new thing with its own unique identity. To really drive this point home, let's look at one final clear-cut experiment. Here we have 2 samples. Sample A on the left is just a simple mixture. We've just stirred some gray iron filings together with some yellow sulfur powder. Sample B on the right started with the exact same ingredients, but we heated them up, causing them to chemically react and form a new compound.
Okay, first test, let's bring a magnet close to both. Watch what happens with the mixture, sample A. The iron filings, because they're still just iron, leap right off the plate and stick to the magnet. The sulfur gets left behind. But now look at sample B, the compound. The magnet does absolutely nothing. Why? Because the iron isn't just iron anymore. It's chemically locked into a new substance called iron sulfide, which is not magnetic.
And this table just sums it all up perfectly. The mixture looks non-uniform, and we know its parts keep their old properties, like magnetism. But the compound is a uniform black solid. It's not magnetic. And check this out. If we add acid, they behave totally differently. The mixture makes odorless hydrogen gas, but the compound makes hydrogen sulfide, the gas that smells like rotten eggs. This is undeniable proof that sample B is a completely new substance.
So, okay, we've gone from mixtures to pure substances and broken those down into compounds and elements. We've really sorted the building blocks of our world. But, so what? Why does this classification matter so much? Well, it matters because understanding it is the key that unlocks pretty much all of modern science and technology.
This is not just abstract knowledge for a test. This is the foundation for almost everything. When chemists create a new life-saving drug, they are creating a new compound. When engineers invent a stronger alloy like stainless steel, they are making a new mixture with specific properties. Developing fertilizers to feed the world's population, that's all about creating compounds that plants can use. It all comes back to this basic understanding.
And the innovation just keeps coming. Take a look at this incredible stuff. It's called graphene aerogel, and it is one of the lightest materials ever created. It's so light it can sit on these delicate blades of grass. And what's it made of? It's made from just one element, carbon, the same element that makes up charcoal and diamonds. It's all about taking a basic element and arranging it in a new, brilliant way to create a material with properties we've never seen before.
So, what's the big takeaway from all this? It's that the seemingly simple difference between just mixing ingredients in a bowl and chemically creating an entirely new compound, well, that difference is everything. It's the foundation for nearly every major technological and medical breakthrough. Which really makes you wonder, doesn't it? What combination of elements, what new compound is out there waiting to be discovered that will completely change our world next?